Welcome back, Contemporary Math. We are in 1C. We are doing sets and Venn diagrams. So we're going to draw a lot of Venn diagrams in this section. And so they're going to start off talking about relationships among sets. So they're going to define a set. And so if I asked you what a set is, it's kind of like literally anything and everything that's out there, right? They define it as a collection of objects, living or non-living. And so when we talk about sets, we'll typically put braces to denote we're talking about a set. And then the other thing that's defined there is members. So members would be the individual objects within the set. So I guess the general thing I could say, like the set of people in the classroom, and then the members would be each student within the classroom, right? So here it says use braces to write the contents of each of the following sets. So the set of oceans on Earth. If I'm being honest, I don't know if I would know all these. I would know like the first two for sure, Pacific and Atlantic. Probably know the Arctic and there's one other one that I would definitely not know if I hadn't looked it up. That's the Southern. So I'm not the best in geography-wise, but there's 5 major oceans on Earth. These are the braces that denote that we're talking about a set. These are the individual members of the set. We separate each member with a comma. So the set of years that Obama was president. So I believe he won the 2008 election. So it started with what, 2009, 2010, 2011, 2012, 2013, 2014. I can't write numbers yet. 2013, 2014. And places, and I'm running out of room on my paper. But we can have a set of numbers. We can have a set that is not numbers. We can have a set that's words. We can have a set that's variables. We can have a set that's numbers. It's anything and everything out there. The set of natural numbers greater than 15. So natural numbers are basically your positive whole numbers. So if we do what, 15, 16, 17, there's a lot of natural numbers that are greater than 15. There's an infinite number of natural numbers that are greater than 15. If you want to go ahead and write all of those, you can. But repeating pattern of going up by 1, right? With an ellipses, it says repeat the pattern. Okay. So this is sort of what sets look like. This is members. And now we're going to talk about illustrating relationships with Venn diagrams. So again, this might seem, well, we did throw in some numbers here, but like a lot of this might seem like, hey, what the heck does this have to do with math? This is kind of all like we do in math. If all of math is, all what we talk about in math is sets and relations. We talk about sets of numbers and how they relate to each other. And pretty much every concept, I think, haven't seen one that can't be deduced to or boiled down to sets and relations. So two sets may be related in the following way. So we talked about sets. Now we want to talk about how they may be related. So we're going to start drawing some Venn diagrams. So some messages about how to draw Venn diagrams. Most people start with the Venn diagram by drawing the box. We want to draw a box. They call this the universe. This is going to represent everything out there. So A is a subset of B if all members of A are also members of B. So we want to draw circles to represent sets. We want all the members of A to be contained or to be also members of B. So all the members of A. There's just some different colors here. So we get like a little bit better. Also be. And so this is the sort of Venn diagram we draw for a subset. So we say A is a subset of B. So if you put your little finger, put your pencil pointer anywhere in A, guess what? You're also going to be in B. That's what this thing is saying. So two sets can be related by being subsets. Two sets can be disjoint. So if A and B are disjoint, that implies that the sets have no members in common. So first we want to start by drawing our universe. We want them to have no members in common. So how do we do that? As the Offspring song, separated. I don't know. Horrible reference. There it is. Okay, so disjoint sets, A is disjoint from B, implies that the sets have no members in common. There we have it, two disjoint sets. And then one other way that sets might be related, we draw our universe. Beep, beep. They can be overlapping. So there is some kind of overlap. Here's A, I'm going to draw it kind of B, but there is some area in the middle there that overlaps. So A and B overlapping set implies that the two sets share some of the same members. So I can put my finger like right here in this part, and it is both in A and it is both in B. So it is both a member of A and it is a member of B. So I probably didn't do that with this, but you can also put your pointer in here, right? If you're in A, you're not going to be in B. If you're in B, you're not going to be in A, right? So these are following the definitions that we provided. So now we want to describe the relationship between the given pair of sets and draw a Venn diagram. So mammals and bipedal animals. So bipedal means you're walking on 2 feet. So are they disjoint? This is going to be the first question. So I think disjoint is probably the first thing that you probably reject from your mind, right? So there are mammals that are bipedal animals. Is it a subset? Is one a subset of the other? Well, there's bipedal animals that aren't mammals, and there's mammals that aren't bipedal, right? And so what this should look like an overlapping set. I really want to take it home. What I could do is variables. Maybe I should write the actual where it's going here. So one of those sets is mammals, one of those sets is bipedals. And this is kind of going at what I was talking about. There are animals. So the universe is animals that aren't mammals and aren't bipedal. There are mammals that aren't bipedal. There are mammals that are bipedal. There are things that are bipedal that aren't mammals. Okay, so now we're going to think about lizards and mammals. Can we have any lizards that are mammals or mammals, any other mammals, lizards? So there's no way we can have a lizard that's a mammal. There's no way that we can have a mammal that's a lizard. Those things are not going to cross. They're not going to be subsets of each other. Okay. And so now we're going to talk a little bit about sets of numbers. Okay. So they talk about, do they give you the names? They give us the names here, right? Whole numbers, integers. So they kind of give you this in order. So natural numbers, whole numbers, integers, rational, and real numbers. Okay, where are rational and irrational numbers found in this diagram? Imaginary numbers. Okay. We're going to talk about the universe. We're talking about natural numbers. Like 1, 2, 3, 4. Next, we talk about whole numbers. And so each of these is a sort of subset. So we start out with a smaller set, and we're just building this thing up and including more and more sort of. So, of what? Integers now? Include negative. Actually have an ellipses going this way. And press 1, 0, 1, 2, 3. And they have an ellipses going that way. And I didn't build my universe big enough. We're going to be bumping into each other. But now we talk about rational numbers. So rational numbers, the key word is like ratio here. These are things that we can write as like halves, right? Another way to think about it is it a terminating decimal? Is it a repeating decimal? Right? 1/3 and repeating decimal. There's a pattern there, right? So that's rational numbers. Oh man, draw another bubble. Now we want to talk about real numbers. So this is anything and everything that's rational numbers. 5, 2. Things that don't ever terminate, things that don't have a pattern, right? Decimals that don't have a pattern. So where are irrational numbers? I kind of gave that dead way when I define real numbers. So there you go. Irrational numbers would be over here in the real numbers. And so real numbers would include rational numbers, integers, whole numbers, and natural numbers, right? We're just adding this to the set. We're adding things like this to the set, is what I'm saying. Okay. Where are imaginary numbers? Well, here's our universe. These are all the real numbers. We actually don't have imaginary numbers on here. The imaginary numbers would be somewhere out here. So you could just put an X. They are things that aren't real. If maybe you know, there's no, I don't believe there's anything other set. So I believe you can write it as just an X out there. Or you could just maybe if you don't know, you could write your own little bubble, say it's not real, right? Then you could create its own little set. There might be other sets out there. I'm not sure. I have to look into that. Okay, so now we have categorical propositions. All S are P, no S are P, some S are P, some S are not P. Okay. And they wanted to give an example. Okay. So come up with an example. All S are P. All cats are feline.
I should specify, like I'm talking about.
That's right. There are other felines out there.
So the subject would be what? Cats. Okay. Dogs are feline. Dogs are feline.
Some S are P. So some cats are colorful. And some S are not P.
Dogs are dogs.
And so we want to think about how to draw these sorts of Venn diagrams. So if I'm looking at this, all S are P. So this should look like this sort of picture. All S are P should be the sort of subset picture, right? All the members are S are going to be contained within P is what this is saying. No S are P. So what is this saying about the sets? This is giving us, hopefully you can see it, is a sort of disjoint set, right? So no members of S are going to be members of P. Some members of S are going to be members of P. So what is that going to look like? This is going to look like the conjoined set. And so this is S, this is P. Overlapping is the thing we're trying to think about. God. So that's an overlapping set. But this is giving us something about a member. There is some S that are P. So this is telling us that there is something that is in there. We know some S are not P. Some S are not P. So I think the thing you're probably thinking, is it overlapping or disjoint, right? Which one am I going to draw on this one? So what you're going to draw on this one, right? But we draw it just kind of just in case. Just in case we have to use it, it's there. Some S are not P. So this is giving us something about an existence of a member as well. This is telling us a member exists over here in S, but not in P. So these are the four sort of pictures that we have, all SRP. So this is kind of setting up the structure of the sets, right? I think these two are more setting up the structure. These are actually telling you something about something that exists in there. Okay, so we're gonna have to refer back to these pictures. So hopefully I can get these pictures on there as well as this. So based on figure 1, can you conclude that some P are not S? So all of S are P. So what is this saying? Can we conclude if there's something out here just based on this information that all S are P? So if we, what this is saying is if we put a X and within the S, it's also going to be within the P. Can you include that there are some P that are not S? Can we conclude that there is a member out here that is not in here? Well, if all S are P, there is actually a case where all P are S would mean that P and S are actually the same set. So if I said this, all dogs are, well, what do I say? What is something that's just anonymous? If I say all students are learning, all students are people that learn, and all people that learn are students. These could both be true statements, right? And if those are true statements, then what we're actually talking about is that P and S are the same set. So can you conclude that there is something out here in P, not in S? And we actually, this is kind of going to be confusing, but we can actually not conclude that, right? And part of why we cannot conclude that there's not something out here is that we don't know that S doesn't just expand out and it's the same thing as P. So that is a weird question, I know. But I won't ask you it again. So figure 2, is it possible that some P are S? So hopefully this one is a little more straightforward. Is it possible that there are some P that are also S? And this one, I hope you look at it right away. They are disjoint. There's no way I'm going to get one member that is also the other. I think that one's a better question. So based on figure 3, is it possible that all P are S? So if we know that some P are S, is it possible that these two things are just the same set and that there's nothing else out here? Based on this, just some P are SRP, it is absolutely possible. So all PRS would look like what? That would actually change the picture to be a subset, right? So all PRS would look something like that. Okay. Based on figure 4, is it possible that no PRS? So no P, nothing in P is also going to be in S. So some S are not in P. Is it possible that there is no overlap here is kind of what this question is saying. And I think I briefly addressed that, but yes, it's possible that these two things are completely disjoint, right? So I know we drew them together, but it's possible that they're completely disjoint. You know, there's an S over here that's not in P. Okay. So example 5. some cars can run on electricity. So they want us to rephrase this. So some cars can run on electricity. Should look like figure 3, right?
Going back to figure 3. Car, electric.
And figure 3 looks like this.
So some cars run on electricity. Some cars.
Are electric. We know there's a member in their overlap. So beggars can never be choosers. So this should look like, we could rephrase this
As what? No beggars are choosers. If we do that,
then it's just figure 2 up there. It's no SRP.
beggars.
And how do we draw these two sets?
With absolutely no overlap.
Okay, so this is sort of Venn diagrams with two sets. The world gets more complicated than just two sets. So we're going on, we're going to talk about three sets here. And we have employed, we have student, we have teenager. So if I put an X here, this is a student that's not a teenager, not employed. If I put an X here, this is someone that's employed, but not a student, not a teenager. If I put an X here, this is someone that's a student and employed, but not a teenager. And if I put one in the middle, it's someone that's what? Student, employed, and teenager. If I go out here, it's someone that's none of these, right? So you hire an assistant to help you with the study of, did we just skip past, is there an example for this one? I guess not, huh? So they're introducing this to you. You hire an assistant to help you with the study of mutant teenage turtles. Your assistant reports the following. Some of the turtles are mutants. Some of the non-mutant turtles are older than teenagers. Put an X in the appropriate place to indicate the regions in which you can be sure have members. So some of the turtles are mutants. So we're going here in turtles. We know that some of them can be mutants. So we know there should be something in the overlap of these two circles. So we put an X right here in the overlap of these two circles. So we don't know if they're teenagers, so we do not put them in the teenagers, right? We put them in the overlap here. Some of the non-mutant turtles are older than teenagers. So some of the non-mutants, so that is telling me it is not in this circle, so I have to stay out of this circle. Some of the non-mutant, they are turtles, but they're older than teenagers, so I cannot put an X in this circle. So I have to put an X in turtles, but not in mutant, not in teenager. Okay. Okay, so now we want to draw a Venn diagram to represent a table data. Let's draw it. And they're looking at whether someone drank coffee and whether they had gallstone disease or did not have gallstone disease. And so we want to create two Venn diagrams, And I think like the first thing people will do is they'll look across here and they'll try to do this with these two sets. Don't do that. We want to create one for this, and we want to create one for this. So one should be for, what is this, your columns, and one should be for your rows, right? And so if we want to do that, one of the Venn diagrams is going to represent columns, and one of them is going to represent rows. So this one, I'm going to go with coffee on this one. So if I go with coffee on this one, I should go with gallstone. Or I should go with no disease. You can also do the other one. Okay, but I want to do coffee and gallstone. So if I look in here, I want people that drink coffee but did not have gallstones. So if I look at that, that is that number 4806. And here I want people that drank coffee and did have gallstones. So that should be 91 in here. If I'm looking over here, I want people that had gallstones but did not drink coffee. So they had gallstones, but they did not drink coffee. And there is one other spot you should never forget. We're talking about the universe of things. I want people that had no coffee and no gallstones out here. So that would be the 14,068. What kind of heathens aren't drinking coffee? Okay. So I think we'll get more practice with that in class, probably. Here we go. Now they're giving us a set, and they're going to want us to pull something off of it. So what percentage of those surveyed own a Nintendo Switch? And I know a lot of you are thinking 15 is not it. There is more to it. These people owned a Nintendo Switch. You also have to look over here. Do these people have a Nintendo Switch? They absolutely do. So do these people, and so do these people. So what percentage of people own a Nintendo Switch? I would have to add these things up. And that would give me 41. So 41% of the people surveyed owned a Nintendo Switch. Okay. Let's do one more. How many people did not own an Xbox? Okay. So for that, what would I have to do? I have to look outside of this circle. So this would be the 25, the 13, the 15, 25 plus 13 plus 15. And then don't forget this little guy out here, plus 3. So what is that? 25 plus 13 plus 15 plus 3 should be giving me 56, I believe. Okay, so we have talked a little bit about the structure of like Venn diagrams and how to set things up a little bit. And we've gotten a good like foothold into probably what we're going to do in the next section, 1D. We're going to start analyzing arguments. So we're going to use a lot of these things with the Venn diagrams and the statements with the Venn diagrams to start analyzing arguments and to start telling whether deductive arguments are going to be sound and whether they're going to be valid. And we'll talk more about that next class. So I will see you soon.